Calculus video 43, related rates, example 2. Okay, so again, go ahead and write down the problem here, pause the video, write it down, come back when you're done. Alright, so suppose that a conical tank, if you're not familiar with conical, it means cone-shaped. Conical means cone-shaped. So you have a cone-shaped tank. Right, a tank that holds something, a cone-shaped tank with the point facing downward. It's leaking water from the point at a rate of 0.8 meters cubed per minute. Okay, let's see if we can draw a picture here. We have a conical water tank, a cone-shaped water tank with the point facing downward. So we've got this cone-shaped thing that looks something like that right there. And it's filled partway with water anyway, and it's leaking water out, right? So from the point, you've got water kind of leaking out. All right, so suppose that a conical cone-shaped tank with a point facing downward is leaking water from the point at a rate of 0.8 cubic meters per minute. Okay, what is the 0.8 cubic meters per minute? That is the rate at which what changes? That's the rate at which the volume of water changes. dV dt, the volume of water that's in this tank, is changing at a rate of 0.8 cubic meters per minute. But think about this. You've got this water in this tank, right? If it's leaking, here in a little bit, you'll have less water. And then you'll have less water, and you'll have less water, right? This should be negative 0.8 cubic meters per minute. Because eventually there'll be no volume. Okay. The tank has a height of 7 meters, so it's kind of like the total height of 7 meters here. The tank has a maximum radius, a max radius of 3 meters, meaning that at the very top, what that means, the max radius, the radius here is 3 meters. Now, I'll tell you this tank, picture it being made out of like concrete or something or whatever, right? Those dimensions aren't changing. The maximum radius of the cone, the total height of the cone, those aren't changing. They don't need letters. They don't need variables. They're just constants. The thing that changes is the water level, right? As the cone is leaking, the water is decreasing. So as the water decreases, there's a couple things that change. The height of the water changes. All right, that changes, so that will get a variable. And as that water goes down further and further, the radius also changes, right? This radius here. That radius also changes, right? If the water level is lower, that radius is smaller. The higher the water level, the bigger the radius. So radius changes, height changes, so that those two are given variables. What we want to know is when the water level is at 2.6 meters, so in our case, when the height is 2.6 meters, what is the rate at which the water level is changing? In other words, what is dH dt? Okay, let's think about that for a minute. Water's leaking out, the water level is dropping, H is changing. Is H getting larger or smaller? It's getting smaller. So when we get our answer here, we should expect dH dt to be a negative rate because the H is getting smaller. So what we know is dV dt, the rate of change of the volume, is leaking out at a certain constant rate. We know that we want to know what happens to the dH dt, that's what we want to know, at height 2.6 meters. So because I want to know dH dt, and I do know dV dt, what I need to find is some relationship that relates volume to height. Right? Volume to height. I needed a relationship that relates volume to height. That way when I take the derivative, I'll have a dV dt and I'll have a dH dt. Well, if you remember the volume of a cone, and maybe you don't remember the volume of a cone, let's just a little geometry lesson here. Any sort of shape that you have, let me side note, right? So separate, we'll come back to the problem. let's say you have a box. The volume of the box is the area of the base times the height. That's how we find volume. Let's say the base has an x here and a y here and a height of h. Okay, the area of the base is x times y, and the height is h. Therefore, the volume is x, y, h. If, however, that box comes to a point, right? So if, let's say, instead of that, it looks more like this. You have the same base, but now that box comes to a point and we have this pyramid. Anything that comes to a point like that, the volume is a third of whatever the original shape was. Basically, if you were to draw the point just kind of, from the original picture like this, what you're saying is the volume in the pyramid part is a third of the total volume, and there's 2/3 outside of the pyramid part, 2/3 of the volume. Okay. In our case, we have a cone. The cone comes from a cylinder. All right. To find the volume of a cylinder, it is the area of the base times the height. Now it's a cylinder, so let's say it has a radius r and a height h. What is the area of the base if that base is a circle? Well, the area of a circle is pi r squared, and the height is h, so the volume of a cylinder is pi r squared times h. If, however, you get a cone, so you get the cylinder, but it comes to a point, it means you only have a third of the volume, and we get the volume of a cylinder is 1/3 pi r squared times h. And that is the volume of a cylinder. Okay, we had the volume of a cylinder. Notice that the volume of a cylinder relates V, that's good, with H, that's good. The problem is it also relates R. And you're like, that's okay, we can figure out R. Here's the problem. If you took the derivative right now, you're going to have to do a product rule. You have not only R, you have R squared, but also, even if you just had R, you'll have a product rule. And when you do so, I'll go ahead and take the derivative. You have dv dt, so this is not right. dv dt is equal to 1/3 pi, that's just a number. In fact, you can put it as pi over 3 if you want. Times R squared, that's a function. H, that's a function. We're taking this with respect to t, so we must do product rule. We must do 2r dr dt, chain rule, times h, plus, leave the r squared, times dh dt. All right, that's f prime g plus f g prime. That's a product rule. Notice what happens is, not only do you get r's in your answers, the problem is we get dr dt, the rate at which the radius changes. We don't know dr dt. We know dv dt. We're looking for dh dt, but we have this extra related rate in there that we don't know. So we can't is a strong word. We don't want to have r in our original equation when we take the derivative, because we're going to end up with a dr dt in there. So I don't want to do that. What I want to do instead is to rewrite the volume equation. This volume is equal to 1/3 pi r squared h. We want to rewrite the volume equation in terms of V and H only, meaning no R's. In order to do that, I have to somehow relate R with one of the other variables, either V or H, and substitute it in. Okay, so I need this secondary equation that relates R with one of the two variables, V or H, and just do a substitution, right? R is now equal to 5H, and therefore I put, instead of R, I put a 5H in, and I work the problem that way. So I have only V's and H's. So we need to go back to our picture at the top. I kind of said I was doing side note, and then I went back into the problem there. But in order to make this work, we need to go back into our equation and somehow relate either r to v or r to h. And I'm going to pick r to h. I think I can make a relationship with r and h. I'll just redraw the picture here. So you had the cone. Well, let's draw it right. There's the cone, bottom facing down like this, point facing down. This was 3 meters, a height of 7 meters, particular water level, and that had a height h here and r here. Okay, and maybe you can see now we have this triangle over here. If you take a look at the triangle, I'll draw it over here first. We have this triangle here. And inside that triangle is another little triangle, say, here in blue. And anytime you have a triangle inside of another triangle, where the two bases, in this case, are parallel, this 3 meters and this r, they're parallel to each other, it creates similar triangles. And in similar triangles, we can set up an equal proportion. Therefore, we have a large radius of 3, a small radius of r, a large height of h, and a large height of 7, and a small height of h. And because these are similar triangles, they stay in proportion, meaning that 3, radius 3 over, say, height 7, big triangle, 3 to 7, is equal to small triangle r to h. And now you can cross multiply. You can say, well, that means that 3 times h is equal to 7 times r. And since I want to get rid of r, I need to solve for it. That means r is equal to 3/7 h. And I have a relationship now between r and h that I can substitute into my volume equation. And that way I can get rid of the r in there and replace it with a 3/7 h. Actually, in the volume equation, v is equal to pi over 3r squared h. I actually need an r squared, not just an r. So r squared is squaring both sides here, 9/49 h squared. So actually, I'm going to take this, I'm going to sub 9/49 h squared into the r squared. Now my volume is pi over 3 times 9/49 h squared, that was my r squared, times h. Or if you work this out, volume is pi over 3, I guess I could simplify that, I'll just leave it, times 9/49 times h squared times h is h cubed. Okay. You might be thinking, well, with a lot of work. Maybe, but the benefit is great. Now we have a volume equation of just v's and h's. So when I take the derivative implicitly here, I'll get a dv dt and I'll get a dh dt, but I won't get an dr dt, right? Because I didn't know dr dt. All right, so now let's take the derivative implicitly. The derivative of volume is dv dt. Pi over 3 and 9/49 and multiply together, that's just a coefficient, that's just a number. So I'll just write them down. Pi over 3 times 9/49. And I'll take the derivative of h cubed, which is 3h squared dh dt. Don't forget about the chain rule there. All right, if I simplify, I see I've got this 3 down here with this 3 there. That's about it. So what I have is, I have dv dt, the rate of change of the volume, is 9 pi over 49 h squared dh dt, the rate of change of the height, which is what I'm looking for. Now I can plug in. Don't plug in until after the derivative, right? So dv dt, that was the volume changing. That was, I believe, negative 0.8 cubic meters per minute. And dh dt, I'm looking to find out what is the rate of change in the height, so question mark. With a height of, let me go back and check what I said up here. With a height of, when the water level is at 2.6 meters, so that's my height, 2.6 meters, with a height of 2.6 meters. And I'm just going to plug those numbers in. dV dt, negative 0.8, 9 pi over 49, h squared, h is 2.6 squared, times dH dt. Alright, if I do 9 times pi divided by 49 times 2.6 squared, 9 times pi divided by 49, sorry, 9 times pi divided by 49, I hit something wrong on my calculator, okay? 9 pi divided by 49, I'm getting about 0.577 times 2.6 squared, about 3.90. So I've got negative 0.8 equals 3.90 dH dt. Solving for dH dt, the rate of change of the height, we take this negative 0.8 divided by our 3.90, and get negative 0.205, negative 0.21 perhaps. Although if I'm doing significant figures here, we'll maybe leave it at negative 0.2. The unit here is the rate of change of the height. That is, in this case, meters per minute. We were in minutes here. So the height will change by negative 0.2 meters per minute. In other words, the water level will decrease by a rate of 0.2 meters per minute, right? Whenever the volume is leaking out at 0.8 cubic meters per minute.